Hello.
Hey, good morning. This is Alan.
Hey, Alan, it's Art.
Hey, Art. How you doing?
Good.
Just gonna enter my participant ID here.
Oh, so oh no, David joined in.
Hi, this is David. Who is
Hi,
that?
David. Art's on the line.
Oh, hey, Art. How you doing?
Great.
Hey, David. Alan's here too.
Hey, Alan. Welcome online. Welcome to the meeting. We're just going to get set up here. I think I mentioned it in the notes, but we are live and ready to go, so folks who are on the line will be able to hear us. We'll just have a sort of opening roll call and some announcements at the beginning of the meeting, and then we will turn it over to you guys. Art, you're presenting first, correct?
I assume so, yes. That would make the most sense, right, Alan?
Yeah.
Yes, definitely.
Okay. And shooting for about 30 minutes, correct?
Right. Yep.
Okay.
And so what we'll do is when it is time to go, we'll go ahead and pull your slides up here, and we can turn over the controls to you to advance your own slides if you'd like. We can also do that here if you prefer.
All right. And just to confirm, so I won't have to share my screen, but I should get control of the slides. Is that correct?
Correct.
Okay. That sounds perfect.
Okay. And then because this is a regular meeting, it's a little different from our regular webcast. Other folks will be on the line, so we can do sort of a live Q&A at the end. We'll probably do a pause and take some questions for Art after your part of the presentation, and then we'll do some more for Alan, and then if there's any for both, we can do that as well. So there should be plenty of time left over.
Okay.
Great.
Any other questions? Are you guys all set?
Nope. I'm going to go grab a cup of tea, and I'll be right back.
Okay.
Okay, sounds good.
Here's coffee.
Yes.
On my calendar. I mean, it is kind of like a Monday. Got the reminder.
And then no, I got it. We got out of the woods. We got home just in time. We drive home, and it didn't last very long. I was trying to die. Definitely by the time we got to I just wrote it. Maybe around
All right, I'm on a webinar, so.
Hey, Dave, Storm, you guys ready to roll over there?
Good morning, Norm. Yep, we're just about ready to go.
All right, I'll give you another couple minutes.
All right, this is just a quick note. This is David Wood from the Chesapeake Stormwater Network. For folks who are on the line that are joining as webcast attendees for our Chesapeake Stormwater Network series, this is part of our Urban Stormwater Workgroup monthly meeting, sort of a joint event this morning. We wanted to give folks an opportunity to join us for our presentation this morning from Art DeGaetano and Alan Cohn. So just a note to folks to please try to leave your on mute during the presentation this morning, unless you are a regular workgroup member. We will have Q&A opportunities where you can chime in, but just as a note, that's sort of how we're going to be going today. So we'll have roll call for our workgroup members, and we will have a couple of announcements before we get into the main presentation. So just sit tight and hang with us for a few. Thanks.
Numbers are still climbing. We're up to 63. All right, good morning, everyone. This is Norm Goulet, Chair of the Urban Stormwater Work Group. I want to welcome you all on this blustery, cold day to the Urban Stormwater Work Group meeting, our January meeting. Kind of ironic today, we'll be talking about climate change when it's about 20 degrees out. Let's go ahead and I'll go ahead and start us off with a roll call. Let's go with just the members of the work group and not so much the CSN webinar folks at this point. We'll jump into that aspect to it later. So starting off with Delaware. Oh, no Randy. All right, District of Columbia.
Cecilia Lane, DOEE.
Maryland.
Christina Lyerly, MDE.
New York.
Cassandra Davis, New York State Department of Environmental Conservation.
Pennsylvania.
Lee Murphy.
Virginia. West Virginia.
Alana Hartman.
Chesapeake Bay Commission. EPA Region 3.
Hey, Norm, it's Liz Ottinger.
Bay Program.
Hi, this is Julie Director Wynn, the Climate Resiliency Work Group Coordinator.
I've got David Wood, Chesapeake Stormwater Network.
Tom Schuler, Chesapeake Stormwater Network.
Gary Shank, USGS.
Allie Wagner, CRC.
Lou Linker, EPA Bay Program.
Wu, CRC.
Jeremy Hansen, Virginia Tech Bay Program.
All stars.
Okay, local government implementers. Virginia.
Casey Filipino, Hampton Roads Planning District. Heather Ambrose, Fairfax County.
Local government, Maryland.
Heather Gawanter, City of Rockville.
Local government, Pennsylvania. Our at-large members.
Ginny Sneed.
Whoever was talking with Ginny, you got overwritten.
Chris Swanson.
Thanks, Chris.
Mark Zagorski, Montgomery County Planning Department.
David, do you want a roll call of the CSN members?
No, I think that's all right. We do a registration for our folks, so we know roughly who's on the line. Thanks, Norm.
Okay. And anyone else on the work group that has not spoken up?
Jeff Lloyd, MDE.
Alex Forrester, VDOT.
All right, looks like we've got Dustin from DEQ. Dave, make sure you get that one. All right, pretty crowded room today. We've got 70 people on the call. It's haven't seen that number in a couple of months. So just good showing. All right, let's start off with David and webcast announcements.
Sure, thanks, Norm. Pretty quick update this morning for our webcast schedule. We're still working on getting some of them on the calendar. Right now, obviously, today is serving as our first webcast of the year, sort of a special event webcast, so thanks for everybody who is joining us for that today. We will have a recording of Art and Alan's presentation available for folks who'd like to download and watch it later as well, so in case you aren't able to stick around. For those who are joining for the webcast portion, we have a couple of other climate change and stormwater related presentations this morning. We encourage you to stick around. This meeting is open to the public, so you're welcome to join us for the rest of the meeting as well if you'd like. We do have one other webcast that is on the schedule right now for next Tuesday, the 28th, at our regular time, 12 o'clock to 1 o'clock in the afternoon Eastern time. It is Christy Hopkins from USGS. For those of you who are on the Urban Stormwater Work Group, we saw Christy's presentation back in December. They've been doing some really good work in Montgomery County to better understand the effectiveness of selected stormwater management practices. Just some really good long-term research findings for folks who are interested. We really encourage you to join us. Like I said, we got a sneak preview of that presentation back in December, and it's a really good one, so I encourage you to check it out. We are working on a couple of other webcasts for the rest of the spring. We hope to have between 8 and 10 before we break for the summer, so keep an eye out for that.
All right, thanks, Dave. Let me circle back to the December minutes. Did anybody have any comments or questions on the minutes? If not, I'll deem them approved. Okay, final announcement. As most of you probably will remember, I submitted a RFP through the GIT process to fund a IDF curve pilot project. Happy to say that project got funded. Not only did it get funded, it got funded in the vicinity of $150,000. I really want to thank Lou and the modeling guys to really putting that forward to help me to get that kind of cash together for this RFP. The RFP went out on the streets. The RFP closed a number of weeks ago. We received 3 proposals. The first was from the University of Tennessee. Second was from Atmos Research and Consulting with a subcontractor for CWP, Center for Watershed Protection, along with the Northeast Regional Climate Center. And the third RFP came in from the Rain Corporation with subcontractors from Cornell University and Carnegie Mellon University. The reviews for the RFP are actually due tomorrow, so I can't really tell you much more than what I'm saying right now. Come next month, we'll have an announcement as to who the respondent shall be, and hopefully maybe we'll get a chance to talk about their proposal. We'll see how far down we get into the selection process if we do that for next month. Does anyone have any questions on that or on David's webcast? Okay. As David mentioned today, we're kind of taking a bit of a dive into some climate change. First off, we've got Art from Cornell University and Alan from New York City DEP. Their work that they put out there on the website that we've actually sent the links out prior are pretty much along the lines of what gave me the idea in terms of what to put into the RFP. So I'm really happy to see them come here today. David, myself, Tom, and the modeling guys actually had a one-on-one with them before we wrote the RFP, and I actually learned quite a bit from these guys. So I'm hoping you guys also will learn a bit. Later on, we'll be talking with David. He'll be giving us an update on CSN's climate. On what they're seeing with the Phase 6 model and climate change. And then after that, I forgot what the last one was. Oh, we're talking about the Q list for BMP crediting. So with that, let me go ahead and kick it off to Art and Alan, and I believe Art is going to go ahead and start us off first.
All right, I'm unmuted, so next one.
We can hear you.
Other one. That's the one. All right. So can everyone see my slides? I don't see them in presentation mode. Is that?
Yep, just give us 1 sec. We're pulling them up now, and we are giving you control so that you'll be able to advance it in just a second.
All right, sounds good. Not often I get control, so that's I'll take it when I can get it, I guess. So welcome everyone. Great to have so many people online. Yeah, it's always tough to give a talk on climate change on a cold day. My class starts tomorrow morning, so I'm going to have to preface it with that as well. So anyway, basically, what I'd like to talk about is a little bit of background for some of the work that we did on looking at future projections of IDF curves. Really, the work was funded through the New York State Energy Research Development Corporation, NYSERDA, and it was a project that was specifically requested by the New York State DOT. And I am not having any advance when I try to do this.
Art, click on the screen a couple times. Usually that will give you control. There you go.
There we go. All right, perfect. All right, so a little bit of motivation about the work that we did. Pretty much started off with kind of this now iconic map to your left, which was part of the National Climate Assessment. which showed at least a metric of heavy rainfall, the heaviest 1% of all daily rainfall events over a period of time. And basically it showed that specifically in the Northeast, and yes, I know some of the states that you all are in aren't represented, particularly Virginia. This is the National Climate Assessment definition of the Northeast. But as you can see, and the Northeast kind of sticks out as really the greatest increase of these heavy rainfall events, having a trend of about 71% over the last half century. Then also maybe following up with that, some of the work that my group did that's shown on the right. Basically here what we did was we took kind of the available record from 1950 to when we did the work in 2009 and broke it up into two periods, you know, the 50 to 79 and 80 to 2009, kind of an equal split there. And then what we did is we did some of the classic extreme rainfall analyses on those two sub-periods and to see how the 2-year, the 100-year, and the 50-year one-day storm changed. So what we are showing here by these box plots is if the later period matched the earlier period, the middles of those box plots should lie on that dark black line at 100%, meaning the values were the same. But what we see is all the box plots, or especially the medians of the box plots in red, fall below that line. And the way you can interpret that is what used to be a 100-year storm in the earlier period, 50 to 79, is now in the later period became a 66-year storm. Say the same thing with the 50-year storm. What would have been a 50-year storm is now a 33-year storm, and a similar reduction in the 2-year storm. So in all of these cases, what we've seen is more extreme rainfall in the latter period, which made had to increase the frequency, the expected frequency of these extreme events. So I'm not going to say too much about this so I don't steal Alan's thunder later, but basically really the motivation here is in New York for certain permits, particularly, and also starting to look at things with stormwater in the case of the city. You know, basically they wanted to make sure that future climate conditions were taken into account, particularly in things related to flooding. And so kind of going back in time, really our work in this area started, probably back in around 2008, 2007, with some work that was funded by the USDA Natural Resources Conservation Service. In New York and New England, unlike points to the south, NOAA had not updated their version of TP40 to Atlas 14 in these states, despite doing that to the south in Pennsylvania and New Jersey and then down into the mid-Atlantic. So there was concern in the region that there were big changes in these numbers in the south. The data hadn't been updated for over 50 years, and they kind of wanted a redo of the atlas covering New York and New England. So we did do that for them, kind of spurred NOAA into doing their Atlas 14 up in this neck of the woods. And our main finding was that there was a tendency in our analyses for the 100-year storms to increase in intensity, and the small increase actually in the 2-year storms. And that's kind of what we might expect with the change in heavy rainfall frequency that we've been seeing. There were some early adapters in the region, and actually, particularly the state of New Hampshire and the state of Massachusetts actually still use this atlas in a lot of their state regulations. And also as part of that, we kind of said to ourselves, boy, it's kind of dumb that these things are only updated every 50 years, particularly in this day and age with computer technology. So we also developed kind of a side project. Really haven't released it to the public. It probably needs a little bit more tweak, but what it allows us to do is actually update these values each year as time plays out. So when the full year of data is complete, kind of in a weird time of year now where we'll update for 2019 in probably about April once all of the data have gone through their quality control. But at least for last year, you can see kind of by the red dots, these are all areas in which the return period of, in this case, the 100-year storm has decreased. So it's now like a 70-year storm since we've done the atlas. And I guess full disclosure, there are a lot of green dots here where there are some places where actually that's lengthened in time. And this just kind of deals with the statistical fitting and how the time series has played out. But far and wide, we're looking at oranges and reds on this map, which again show more extreme rainfall. The other thing that we did was kind of looked at, this is, I apologize for this graph, it's kind of more to remind me to say something. But we also kind of were challenging the premise of when we do extreme rainfall analyses, we should use the longest period of record possible. And that used to be good advice back when we could assume a stationary climate. But with the trend that we've been seeing in these extreme rainfall events, really what you want to see in this graph is for all of these lines to kind of cluster together. So where they start to spread apart, that kind of gives us some concern that the trends we've imposed in the data, whoops, it's being a very sensitive there, oops, sorry. Basically in this case, we've taken series that represent real stations and added trends to them. So as you go from the gray to the red to the green, the trends there are more severe. And what we see is for something like the 5-year storm, these start to kind of diverge at around 70 years. You see the same type of thing, maybe around 80 years for the 10-year storm. And as you get out to higher storms, it takes longer periods of record for them to diverge. Kind of there, what that says is for these long 100-year, 50-year storms, maybe using a long record isn't that bad. But when you're concerned about maybe things more on the 5 or 10-year storm, that long record really works against you when there's a trend. And you should maybe be looking at something on a 50 or at most 80-year time frame, which many of our stations do have these days. All right. So kind of to take a jump there and say, how do we go to the future? So basically, it involves looking at climate models, and it involves a process that we call downscaling. So sorry about the Massachusetts map, but it was the one I had easily available. If you look at the upper left corner, basically what's shown there, the kind of boxes that are shown, that's the typical resolution of a global climate model. So they're on the order of about a degree of latitude by a degree of longitude. So we kind of look at the intersection points across Massachusetts as maybe places where we would have data. You know, if you're a purist, you say, well, there's really only one that falls within the state. And maybe if you count these ones in Upper Connecticut, you have about 3 values for the entire state of Massachusetts, which again, similar in size to Maryland or something like that. The dots on all of these maps are the station locations. So these are locations that have good long-term records that we can use for extreme rainfall analyses. If I go to the graph or the map that's on the right, that's basically the typical resolution of a data product that's been downscaled using dynamical downscaling, or actually even some of the statistical downscaling techniques. It's about 1/4 of a degree of latitude. Maybe on the, you know, if we look at rough numbers in this neck of the woods, about 30 kilometers square for these grid boxes. And again, you can see it obviously increases the number of points within the state, but still not a great representation of all the stations. You know, maybe we're talking about a half a dozen to at most 20 grid points across Massachusetts. And then if we further downscale this to, this is a 4-kilometer grid. This is typical of some of the gridded observed data products. There are some downscaling techniques that will get you down to this resolution, but in my opinion, it's really no more than kind of dicing the onion finer. It's really hard to gain more information, particularly if you're doing something statistical in this regard, particularly given the distribution of stations. It's really the stations that are guiding this downscaling. So our work for New York, what we did was actually employed or looked at 3 different statistical and dynamical downscaling approaches. The first one uses a data set that's called Cortex. Basically, what Cortex has done is downscaled 4 of the global climate models with a set of regional climate models. So basically here, the best way I can describe it is the global models provide the input, the global models at a 1 degree resolution provide the input to a finer scale model at the regional scale that knows things more about topography or bodies of water and things like that. Again, to maybe give you an example, the majority of the global climate models do not know anything about the Great Lakes. So if you're going to get any of the processes that involve the Great Lakes, like the lake effect snow that we saw up here this weekend, you really need to feed those data into a regional model that can specify that the Great Lakes are water, look at the topography coming off the lake shores, things like that. This is typically what's done in weather forecasting, and it's been extended to climate modeling. There's also an earlier product called NARCAP. It was based on the older generation of climate models, and I won't present any of the results from that, but we did look at that as well. Then we looked at 2 statistical downscaling methods. The first one is about as simple as it gets. I'm going to call it the delta method. And really all it does is at the global scale compares the model simulated precipitation extremes in the model's historical period. So the global models do simulate kind of what went on or what should have went on in the past. The delta is the difference between their portrayal of the extreme precipitation climatology in their historical period versus what's going on in the future period. So there you get a difference or a percent difference between the model, and that is something that you might apply to the observed data at the station to get a future change. And then, and then also we looked at a kind of a different statistical downscaling technique, which I'm calling the analog method here. And what we did here is instead of looking at rainfall itself, we looked at patterns on weather maps and tried to see how often do the climate models in the future kind of project patterns, simulate patterns that produced heavy rainfall in the past. So we'll talk about that in a little bit as well. So now for our reality check. So the first thing we did was basically saw how well the models in their historical period corresponded with actual observations. So all of the next couple of slides are going to look very similar to this. They're showing bias along the vertical axis. So if kind of a ratio of the historical model data to the observations. So if they're a perfect match, the box plots would fall on the 1-to-1 line, or the horizontal line here at 1. And basically, as we move upward to that, it would show that the models are overestimating the obs. And if we go underneath that to the values less than 1, the models are underestimating the observations. The different colors here are the 20-some models that are global models that are included in the CMIP-5 archive. And basically what we're showing here is the bias. The box plots themselves, the range of the box plots, are actually stations in New York. So there's about 75 stations that go into these box plots. So what we see basically overall is the models at this scale are underestimating the station extreme rainfall, which isn't a surprise because we're working at a very high, a very coarse resolution grid here, 1 degree as opposed to the station locations. Most of the models are consistent in that bias, somewhere between 60 and 80%. And if I point out the gray box plot, that's kind of the model average, the model mean. So about a 75% underestimation of reality. And keep in mind, the only reason we're really doing this is in that delta method downscaling. So what we would say is, you know, we would take this underestimate and then look in the future, and presumably the values would be higher. They still might be below 1, but we'd look at the difference between the model's future and historical period. If we look at the dynamically downscaled values, here in Cordex, there's basically available 4 kind of combinations. Basically, the second values, the CAN, ESM2, let's say, and the EC Earth are acronyms for the global climate models. And then the first acronym are regional climate models. So basically 3 different regional climate models applied to 2 different global models. And we can see, depending on which ones we choose, they're either overestimating the historical period or underestimating the historical period, but on average, actually not doing all that bad as well. Kind of, we would expect that box plot to be sort of where it is there. And then finally, a bit of a description of the analog approach that we employed. Basically, the idea here is from the climate model at the coarse climate model resolution. Basically, we have a weather map, and here we're looking at not temperature or precipitation, but where the highs and lows are, how much vapor transport there might be at upper levels of the atmosphere, kind of the ingredients we need to produce extreme rainfall. And then from there, we take each of these climate simulations for some future date, notice this is 2055, and try to match it to maps that actually occurred. So if you can see, this is, you know, 1995 and 1972, etc. And from there, you can kind of develop a regression equation to say, boy, the future low resolution map is this combination of historical dates. You know, these are for different days. And then what we can do is on these historical days, there's actually a finer resolution of these maps because we have the data. It's not at the climate model scale, but we can kind of almost use it at that 4-kilometer scale if we wanted to. And we would apply this relationship to these maps now using the precipitation to get the future day map. So we can say, oh boy, on all these historical days, we might be looking at rainfall in this case. This is what we get for that future day. So we kind of take the weather pattern at a coarse scale, apply that relationship to fine scale weather maps in the historical period to get what we get in the future period of time. And when we do that, again, I'm looking at bias, same color scheme. I happen to be looking at a 1-day 5-year event here. That was the case in all of the previous models. And, you know, I'll leave it to you, but I guess in my biased opinion, the analog method does really, really well at simulating these historical patterns. The model mean is almost centered perfectly on the bias of 1. Some of the models hit it spot on, and there's kind of some minor about 10% or over or under estimation. So kind of confident in our analog approach. It's probably not the cure-all approach, because I guess the one caveat is the analog approach can only simulate days that have occurred in the past. So in other words, we might have the 100-year storm or a storm that produced a heavy rainfall event once in that historical period, maybe occurring several times in the future period if that happens to be the best match in terms of a pattern. But what can never happen is we can never have more rainfall than that. So if, you know, it's as best as we have more frequently occurring big events that have occurred in the past, but none of them can be any wetter. So if anything in this approach, we might be underestimating what might occur in the future because of that. All right. if we look at New York and kind of look at these biases across the state, so here basically I'm doing the mean bias across all of the different downscaling approaches. What we see is really two things. In the mean, the bias isn't all that large. The kind of light blue and the light pink are right around 1. The darker pinks are actually about a 90% or about an 80%, 80 to 90% underestimation of the bias. The point that I want to make on this also is it doesn't change that much across the state. That it's not like it's not like these individual boxes at the resolution we've done it at are going between the dark blue and the dark red and in between, but it's kind of no matter whether we're on Long Island where there's a strong coastal influence or in the Adirondacks or along the lake, we're getting similar biases. All right, so let's kind of jump ahead and look into the future now. So what I'm showing here is I switch gears with colors, and then basically in the next 3 or 4 slides, green is going to be this simple delta method where I take the global model's historical period and I compare it to what happens at that scale in the future. The red is our analog approach, which I just mentioned, and the blue is this Cordex dynamically downscaled values. And what I'm showing here is the percent change in precipitation across stations in New York. So again, the box plots represent the 75 stations in New York, so what their percent changes specifically at those locations. And I'm looking at a 5-year event to the left and a 100-year event to the right. And I think I did mention it's a high emissions scenario, RCP 8.5, and really in the near term. So actually we're kind of centered on that point right now. Each of the model's historical runs ended in 1999. So that's why I'm not calling this a historical period. This is actually a period that is simulated by the models. So what do we see? The box plots align pretty nicely. So maybe some greater spread if we're looking at the dynamically downscaled Cordex. But all in all, I would say the means of these are kind of lying along maybe about a 7 to 8% increase in extreme rainfall among the stations. And again, I'd like to point out that that's really what we would expect theoretically. There is a strong thermodynamic relationship called the Clausius-Clapeyron equation, which basically relates the amount of moisture in the atmosphere to temperature. So the warmer the atmosphere is, the more water vapor it can hold. And kind of keeping in mind this water vapor in the atmosphere is the raw material to produce the extreme rainfall. So basically, according to the Clausius-Clapeyron relationship, for a 1 degree increase in temperature, we should see a 7% increase in rainfall. And really, we've kind of seen this almost a 1 degree increase in temperature between the historical and in the future period in this case. So not only does this work out well with each of the downscaling approaches, it kind of has a theoretical basis that's what we're looking at. Kind of if I were looking to do projected IDF curves, or even not even project them, but look within a confidence interval or something like that, I definitely go with that relationship as Clausius-Clapeyron as my minimum. If we kind of jump ahead and look basically further out, so this is kind of mid-century, centered on about 2050 in this case, 2055, so a mid-century high emissions. Start to see a bit of a difference between the different downscaling approaches. Kind of again, they're all maybe falling in about 15% of an increase across here. The Cordex experiment showing a much greater range among the stations. The simple delta method showing little change among the stations. And again, to kind of root this in what's going on, we're looking at New York, we're looking at the scale of a global model. So we really only have about 4 or 5 grid points to work with. So even though we're looking at the station scale, they're all relying heavily on what's happening at those 4 or 5 grid points. So it's not surprising that the spread among the stations is not that great. And when we look at the analog approach, it's actually the smallest percent change into that future period at about 10%. And again, very similar change whether we're talking about a 100-year storm or a 5-year storm. And then finally, if we go all the way out to the end of the century, 2070 to 2099, again, everybody raises up, still kind of get that same pattern of Cortex, the dynamically downscaled data giving us the biggest changes, the simple delta method giving us a middle of the road method, and not much spread among the stations, and our analog approach actually giving us the lowest change at about 15%. A very similar progression of how, you know, the percent change, we go up by about 5%, as does the Cortex experiment, and as does the delta method in this case. So really, that's what we show from these different downscaling approaches. What we did in the end to get our I can also show that as maps, but what we did in the end is really combine together all of those approaches. So not only did we look at many, many models, but we also looked at the different downscaling approaches. And when I say starting to look at, say, an ensemble mean, I'm looking across the models, and I'm also looking across the downscaling approaches. So that's what these maps would represent when we're looking here in the middle, the mean change across New York. That's the mean of all of the models, all of the global models, and all of the downscaling approaches. So it's kind of like talking about several hundred values going into that mean. And what I'm showing here is out of that many downscaling approach climate model combination, I'm showing the average, the 10th percentile, so the smallest change, or the 10% smallest change, the 90th percentile, so up at the high end of that distribution of change. I'm showing the low emissions scenario across the top, RCP 4.5, and the higher emissions scenario across the bottom. So if we look at the mean across New York, really no difference where I am basically in a high emissions scenario, and kind of on the order of between 15 and 30% change. If I look at the lower emissions scenario, again, not much change across the state. One might argue a little bit higher out on Long Island, but you know, we're pretty much splitting straws here between these large bins, and a change of about 10 or 15%. Whoops, let me go out. And again, keeping in mind, this is the end of the century. If we go to some of our higher changes in the models, that idea of a coastal to inland difference also kind of shows up in a couple of cases with higher changes along the coast and less changes as you move inland. So in a high-end scenario, we're looking maybe as much as a 60% increase in the one-day 100-year storm out on Long Island, and more like a 40 or 50% change in central New York. So we basically moved on to this. We presented this to New York DOT, and then basically developed a website in concert with them. So we'll dive into the IDF curves a little bit more detail in the next slide. But basically, you can see on the left is really the navigation. The dots show the stations that went into the analysis. As each of the dots, you're able to select your return period that you're interested in, and that'll change what IDF curve you're interested in. I happen to be looking at a 100-year storm here. You can select between the two emission scenarios, higher or lower, and then you can select against a time period that you're interested in, the near term, mid-century, or the end of the century. the IDF curve also comes with a table that shows the values for set durations. So I'm going to go to the next one here, kind of a blow up of that. So again, intensity, inches per hour across the vertical, duration in hours across the horizontal. What we're showing here is in the kind of pink band, the black line is the projected intensity duration at these different timescales in the future. So I'm looking at the end of the century here. The pink area is the 80 percentile range of the model projections. So that kind of 10% to 90% that I showed on the other graphs. And then in the blue with the dashed line is the value that we get for this station based on the observation. So it's the observed period of time along with the 90% confidence interval in the blue. So what we're showing here is what's projected to happen in the future, kind of alongside of what we're kind of working with now in terms of a historical period of time. We do this historical period two ways. One is we do things a little bit differently in how we fit distributions and do things statistically compared to what NOAA has done in Atlas 14. So we kind of do that both using our projected data and our historical data. So this is more of an apples to apples comparison in terms of the same statistical methodology applied to the observations in the climate model projections. But what you can also do back on the other screen, and I didn't have the right one there, but there's a box that you can check to actually show the Atlas 14 values. So for each of the stations that you can choose, we went into Atlas 14 and got the actual values. So you can see the actual Atlas 14 from NOAA values superimposed on here as well. Again, values here for the durations, so in a tabular format or a graphical format. I think two things to hit on this. We are only using daily data. So even though these durations, hours are going back to sub-daily values, we did not dabble in that with our climate model projections. Keeping in mind, most climate models work on a daily time step, and it would be hard to also downscale these values to say a 1 hour resolution. However, what we did do is sort of some reality checks where even in Atlas 14 or its predecessor TP40, there is an empirical relationship whereby you can adjust, say, the 1 day, 24-hour, 100-year storm to a 12-hour or a 6-hour or a 2-hour storm. So those empirical adjustments have been applied in the past, and what we did was looked at those and tested how well those apply to more recent data. And actually those empirical relationships have been remarkably consistent through time and also remarkably consistent across the country in different climates. So that kind of helped us increase our confidence that we could apply those and look at future periods of time. Some more recent work that we've been doing is we've actually been kind of replicating our one of the earlier slides that I showed you where we broke the period in half and looked at the 100-year storm, 100-year 1 day storm between the two periods. And when we do that with hourly data, actually we find very little change. So again, kind of giving us some indication that the changes some very preliminary indications that the changes at the hourly resolution might not be quite as strong as we're seeing at the daily resolution, but that's really work in progress. What else did I want to say? I'm gonna just another way, again, in working with this, we also picked up by some other kind of stakeholders. In this case, this was the Port Authority of New York and New Jersey, where they were not really interested in the IDF curves, but what they wanted to do is look at a given rainfall amount and look at the probability of exceeding that rainfall amount in different 30-year periods. So we're looking at a 7-inch event in 24 hours at Central Park. The dashed line is what we would expect from observed. The gray area is what we would expect from a confidence interval about that observed period. And the bars and the whiskers kind of show how that changes from kind of now to mid-century to the end of the century. And really here, the probability of exceeding 7 inches in a day starts to be concerning. We start to come outside of this realm of what we expected in the historical period, mid-century under high emissions and end of century under either emission scenario. So I think that about uses up my time, and I'll let David see if we're gonna ask questions or move on to Alan.
Do we have time for a couple quick clarifying questions? Folks have them? We have one in the room.
Great presentation, real pathfinding. And slide number 2 was a wow. I mean, you were showing from observed data from 30-year period, 1950 to 79 to 2009, a 100-year storm becomes a 66-year storm. And later on, you describe what that means in volumes, and the volumes are huge, especially if you're New York DOT and trying to design culverts or bridges. So here's the question. This is all great work. But what if one was to say, let's do everything proposed here, getting things up to a current period, but what if there was for example, a big stormwater facility or culvert design or really any big structure that was expected to last for maybe a half a century? What would be the value of combining the trend information with the GCM information, with the appropriate downscaling you're showing now, so that if, for example, a project was to last for, say, a half century life, you would be able to use a projection that would be based on the observations and the GCM projections. Does that make sense?
I think to a certain degree, yes. I guess I would advocate very strongly for what I would call this kind of hybrid approach that you're suggesting. In other words, I feel very strongly we should be monitoring the trends that we see in the observations, right? That's the thing that's gonna hold our feet to the fire for the projections and things like that. Right. And kind
Agreed.
of, we definitely have been doing that. That was kind of that map that I showed you here.
Yeah.
Wrong way. That map. One thing that I think this needs some work, but that is exactly what we're doing, and you can see it in a graphical format as well. So that idea is each year consistently going up, and you're approaching even the ends of your confidence interval. Once you pop out of that confidence interval, right, I would say, boy, that's when you really have to update these atlases. And by looking at that superimposed on what the models are saying, I think that gives you just increased confidence that you're moving in the right direction. The one place where I'm a little bit leery is, again, if you're saying take the observed trend and extend that 50 years into the future, I would be worried about that, because no guarantee that trend is going to continue to that. That's kind of where the climate models start to kind of keep the feet to the fire in that case.
Yeah. No, the suggestion is along the lines of the engineering communities used a half century to base these IDFs on, and if we were to preserve that half century long-term record and then use a blend of trend plus ICM, maybe we'd be able to do that in terms of providing guidance to the engineering community. And I think you've clearly provided insight in how this could be done, and done well. So one last question: how long did it take from New York DOT to say we want this thing to us seeing this thing? More than a few weeks, I guess.
More than a few weeks, yeah. I think I'm drawing a blank. I think the length of our project was we had a 2-year contract with them, so
yeah,
we did
a lot
this
of work
over
in 2 years.
the course of the 2 years. The majority of the work that we did was actually with the downscaling and things like that. Actually, if I were to do this now, there's a lot of people have done the downscaling. You can almost download those data yourself. So I think that would be a lot less of the work, although we haven't done that with our analog approach, which I think has some value to it.
Yeah, I'm going to save this next question for the next presentation because I know it's a question blizzard, but I'd be interested to know how widespread the adoption by DOT and others in the Empire State is, but we can hold that depending on David's patience with me.
Yeah, we'll take
cut Lewis off.
Yeah, we'll take if there's time for one more question if someone has one for Art, and then we'll move to Alan and we'll catch a few more at the end.
Hey, Art, this is Norm. I got to say that I love the website that you guys put together. I've shown that to a number of local government implementers here in Virginia, and they all absolutely loved it and said, we need this. So consequently, I did write that into the RFP, but I just wanted to tell you in person that that was a great thing that you put together there, and for the local government implementers, it's right online.
Well, that's great to hear, Norman. I guess I know also a call out to, wasn't all our ideas. In other words, New York DOT had a lot of input into exactly what we were showing and things like that. So I think in a project such as that, that's a really critical thing where it can't be me here sitting in my office with my staff kind of doing this, but we had a number of check-ins and reality checks and things like that with DOT in terms of how they wanted the website and also ultimately how they implemented it. And I think Alan will talk to that as well, but I think they took a not very, and I don't mean this in a negative way, kind of looked at the state and kind of said we need this type of an adjustment factor. So we'll see if that comes out in Alan's talk.
Yep. All right, with that being said, let's go ahead and kick off with Alan, and he's going to talk about the New York City Climate Resiliency Design Guidelines. And also, I'll state up front that it was also a very good document. In as much so that I've directed some of my staff here who have been working on various aspects of climate resiliency to tell them, I want to put together a document like that for Northern Virginia. So with that being said, Alan, why don't you go ahead?
Great, thank you. Can you hear me okay?
Yep.
Excellent. All right, thanks Art for your presentation. We've really benefited from the work that Art's been doing, and it's always a pleasure to present with him as I was one of his former students. So I'm going to be talking today about climate change planning for stormwater management in New York City. As was mentioned, I'll touch upon the climate resiliency design guidelines that have been developed by the mayor's office in partnership with us, the New York City DP, over the past couple of years. This is about a 10-year timeline of work, but I'll say that it's still very much evolving and very much a work in progress, and I think there is always room for improvement. So I'm eager to stay tuned into your efforts down there and hopefully learn some things from what others are doing as well. So let's see if the slides are advancing here. There we go. I'm going to start by touching upon the observations on our local climate and the protections that we anticipate, and then dive a little bit deeper into the precipitation projections based on some analyses that we've done, as well as our interpretation of the projections we've received from the Northeast Regional Climate Center. I'll talk about briefly the impacts on our stormwater systems, and then how we're applying the projected IDFs in practice. And then finally, just touching upon some sort of next steps and opportunities for using intense precipitation information in our planning processes. So, like many areas, our temperature has been increasing historically at a rate of about a quarter of a degree per decade. These are the observations from Central Park, which go back to prior to 1900. Mean annual precipitation has increased at about 0.73 inches per decade. You can see, though, we have a market shift around 1970, where the interannual variability is especially pronounced, with years all the way up to 80 inches, and then more recently in 2018 over 60 inches. So we see this trends in annual precipitation seeming to increase. Sea level rise records have been kept at the Battery, also in Lower Manhattan for some time, and we've observed an increase of 1.2 inches per decade, which is nearly twice the observed global rate, partially due to land subsidence, but other local factors in sea level rise. So we rely pretty heavily in New York City on the New York City Panel on Climate Change to provide us information both on observed climate trends as well as projections. This is a really huge asset for us, such that we don't have to typically go searching for the best source of climate information. It also allows us to have consistency amongst city agencies, which is becoming more and more important as more and more agencies are incorporating climate projections into their work. So the New York City Panel on Climate Change is comprised of these institutions, as well as a few others, I believe, on the bottom of the screen, but is actually currently being reinitiated or looking for new members. I believe that call for new members is actually still open, but it's been in place since about 2008, since former Mayor Bloomberg, and refreshes their projections and their reports about on the similar cycle as the Intergovernmental Panel on Climate Change, to be consistent with that. And we have the advantage of some, really world-renowned institutions and local climate modelers, for instance, at NASA GIST. So projections are that temperature is going to continue to increase, with particular impacts on the number of days above 90 degrees, which could triple by 2050. Annual precipitation is projected to increase by 4 to 11% by 2050, but I'll talk about that more. One thing that's been missing from these projections is precipitation intensity, and that's where we've relied on the work that ART's been doing. Sea level rise is expected to increase between 11 to 24 inches by 2050, and the latest NPCC report has a pretty startling sort of consensus-based projection for the Antarctic rapid ice melt scenario, that the high-end projection could be as high as 72 inches by 2100. So this has some very real consequences, not just for coastal protection planning, but the functioning of our stormwater infrastructure. So these are some of my own, hopefully, informed observations on projected impacts on our systems. Flooding is most affected by rainfall intensity and receiving water level. We have about a 60% combined sewer system in New York, and so combined sewer volume and frequency will change with both rainfall volume and intensity. So the impacts, although they vary by location, will be somewhat, I'm not necessarily going to say proportional, but at least related to the increase in precipitation. And sea level rise has, somewhat odd counterintuitive effect in that it can actually decrease combined sewer overflows due to tidal locking of the tide gates, which are meant to prevent backup of salt water into the system. But it is also essentially removing the reason that the combined sewers are there in the first place, or the overflows are there in the first place, which is to provide relief to the system to prevent backup and flooding. So sea level rise has some sort of mixed impacts for us. So I'm going to shift to talk about precipitation IDF curves. This old image is really the impetus for a lot of our work, is that when we started as an agency to really embark on our climate change work in earnest in about 2004 or so, it was really startling to see that we were still using precipitation intensity information from 1903 to 1951, which was the Weather Bureau's last analyses to date until about early 2010s when NOAA Atlas 14 came out. We use this in sewer design and construction and sizing of on-site detention systems. We also use a single curve citywide rather than a separate curve, for instance, for each of the boroughs, just for simplicity purpose. And application is really focused on short duration, high frequency events. Due to the time of concentration of water getting into our sewers in relatively quick time in this urban setting. So in 2011, we embarked on an analysis. Again, this is pre-NOAA Atlas 14, where we looked at hourly data for 10 stations, including 4 stations with 15-minute data, and Central Park going back to 1876. And we found that there was no statistically significant trends in the daily or hourly maximum rainfall, and no statistically significant trend in the recurrence of large rainfall events compared to the 1903 to 1951 curve. We found results to be similar to existing IDF curve, as I just mentioned, from 1903 to 1951. And in practice, we've actually been using this approximation, which is 125 over T plus 15, where I believe T is the time of concentration. And that had, if you look at the dotted line compared to the red line, particularly at lower durations, that approximation had always been a somewhat conservative estimate of the intensity, and it really starts to diverge from the actual curve when you get to the longer durations. But in practice, we don't actually use that too often, again, because we're most concerned, for the most part, with the sub-hourly durations. Since that 2011 analysis, as I mentioned, NOAA Atlas 14 has come out. We've had the benefit of the analysis we just heard about for IDF projections for New York State. And we've also had continuous analyses of daily rainfall from the New York City panel on climate change. I'm not sure actually if it's been updated since 2015 or whether they've carried, I believe they've, in the latest report, they've carried forward the 2015 projections. So the curve for the historical IDF analysis, when we overlay Atlas 14 and the 90% confidence interval, is actually pretty similar again to the analyses that we did. When you start to look at the upper end of the yellow shaded area, your 90% confidence interval upper end is higher than the existing curve, obviously. And one of the potential, applications of NOAA Atlas 14, although we haven't moved in this direction, is that in the future we could move towards, if we're not using the precipitation projections, we could move towards just using the 90%, the upper end of the confidence interval for Atlas 14 in practice. Rather than this kind of usual refrain that we've been using, that the approximation and the curve closely matches the observations, and therefore we don't need to change. So we're not at that point yet. We've been still pushing to move towards the projections, which is what I'll talk about next. So, as I've mentioned, there's been a push not just towards consolidating climate information in New York, but actually consolidating the way that we use it. And especially since Hurricane Sandy, numerous city agencies have been using, at certain points, their own interpretation of the New York City panel on climate change and other projections into implementation. This report on the left is the New York City Wastewater Resiliency Plan, which my agency produced after Hurricane Sandy, and this really focused on protecting our wastewater treatment plants and pumping stations from sea level rise and storm surge. And again, we used the New York City panel on climate change projections. This report actually did feature a recap of some of the early analyses that I just described, and it appears somewhat hidden at the end of that report in chapter 4. But because of the focus on storm surge and sea level rise after Sandy, that's really what the bulk of this report is about. Starting in about 2017, the city, led by the mayor's office, put out its first climate resiliency design guidelines, noting that different agencies were interpreting projections differently and seeking to provide some sort of guidance, consistent guidance citywide. And we started working with them pretty closely because of this question regarding extreme precipitation. The guidelines covered sea level rise, heat impacts, and precipitation. And DEP at the time, had really done the most work on precipitation. So looking at the projections for the IDF curves, and if I'm mischaracterizing anything here, Art will correct me later, I'm sure. We overlay the RCP 8.5 projections with the existing approximation to the IDF plus NOAA Atlas 14. And one thing that you'll really note is that applying it to the existing curve, there's this very noticeable gap at durations below 1 hour. And Art provided some of the reasons why, and maybe we can go into a little bit more detail later, but this was really important for us because we weren't really sure what to do. Again, there's different approaches. You can take the 90% confidence interval for Atlas 14 and use that. You can extrapolate the curves that Art produced, and we had some conversations with him about whether we should do that. but in practice, we came to a little bit of a different approach, and then I'll talk about that in a second. So this is version 3 of the guidelines that came out in March 2019. And again, the approach has evolved over time, especially as it's been used in practice. It's meant to guide city agencies as well as others that want to use it. They are guidelines. They're not mandatory at the moment, but they may become mandatory. And there's some considerations for how they might change if that's the case. What kinds of projects, buildings and infrastructure, new capital construction and major rehabilitation, coastal protection projects and private developments are not included. Coastal protection projects, for instance, are often guided by FEMA or other guidelines. So it's really meant to focus on other on other types of city investments by different city agencies. So the approach that we took in practice was sort of informed by the projections, but rather than extrapolate it or rather than use the IDF 90% confidence interval, we compared the projections to what we use for currently, and found that the 50-year interval was the 50-year IDF curve was a reasonable approximation for what a 5-year future IDF curve might be. And I think that's a little bit overstated. I actually think that it came in higher than the projections. But we continue to use existing precipitation observations, but just use a higher, or rather a higher recurrence interval storm as an approximation for the future 5-year event. And the 5-year event is what we use in practice for sewer design and some of our on-site detention. And like the 125/T plus 15, in practice we use an approximation for estimating the 50-year storm, which is shown here. So the guidelines, and I don't necessarily need to go into this for the sake of time, and also people can read them on their own, but it's essentially instructing agencies to conduct a sensitivity analyses using the 50-year storm instead of the current 5-year, looking at opportunities to maximize retention and detention. This doesn't apply to conveyance in this case because it's only on-site stormwater systems. And given the opportunity, agencies should be considering both higher and lower. So it's fairly flexible, and again, not mandated at this point. But its intent is to really get people to maximize opportunities for holding water on site. This is a little bit more choosing the right combination of interventions after considering the project type, site location, cost benefits, etc. Looking at strategies that infiltrate, evaporate, or reuse rainwater, but also protecting your property, protecting areas below grade, and operational protocols such as keeping catch basins clear. So infiltration practices in New York City currently look like this. We have thousands of rain gardens distributed throughout the city. We have rooftop farms that are funded by a grant program and playgrounds through a partnership with the Department of Education. But these are not designed, these are consistent with the guidelines, but they're really designed for combined sewer overflow. So they're not necessarily designed to mitigate flooding and very intense events, but rather to capture as many smaller rainfall events as possible to reduce the impacts on combined sewer overflow. This is juxtaposed to some emergent practices. This example is from Copenhagen, who we've been working with for the past several years, where their green infrastructure practices are based on managing these really intense events They've got a series of practices going in throughout the city. About 300, I believe, are in planning. And they go beyond infiltration to create these spaces that can flood, as well as actually rerouting water into these areas rather than just passively accepting whatever runoff comes from the street. So we embarked on a project a couple of years ago to actually apply to see what a similar approach as Copenhagen would look like in the New York City context. And we did a conceptual study in an area of Southeast Queens, just north of JFK Airport, where they have continuous, repeated rather, flooding over the years. And looking instead of just, additional conveyance, which is in the planning and it'll take decades to build out, can we also use green approaches to mitigate flooding? And so those two pilot projects, I guess I should highlight, are really where we're testing out this approach. But the idea is that you have a network of green infrastructure rather than distributed practices throughout the city. You want to create a connected network of both infiltration, conveyance, above ground conveyance, and storage. So we looked at the projections based off of what we had from the Northeast Regional Climate Center, and looked at the middle of the century. The 50-year design storm is 3.33 inches in an hour, was a little bit too high for us. We did look at the sensitivity and analyses and the cost and the available storage capacity for our pilot projects. So we settled on a 10-year storm, which is about 2.3 inches. Just for some context, our current green infrastructure infiltration-based systems are designed on about an inch and a half of rainfall and just infiltration. So our pilot project is, one of our pilot projects is located at the New York City Housing Authority South Jamaica houses, and where we would typically do standard infiltration practices. Instead, we're looking to create a connected system of BMPs by lowering some of the grassy areas and putting storage under this basketball court, and actually lowering the basketball court itself so that these areas can actually fill with water rather than just convey or rather infiltrate the first inch and a half. So this is something, it's really one of the first projects that we have, demonstration projects, to incorporate these higher intensity events, and hopefully we'll see some success here and can replicate it in other parts of the city. The one other pilot project we have is in the right-of-way, where we have a low spot that floods frequently, and there's a pumping station that doesn't keep up with typical rain events. And taking some of our cues from what Copenhagen's doing, instead of just putting green infrastructure in the places where it floods and accepting whatever runoff happens to fall, we're actually looking to put in green infrastructure, but recontour some of the streets to divert flow away from the areas that flood. We're also looking at using raised crosswalks as a way to keep flow out of those low-lying areas. So again, this is a slight variation on a theme of green infrastructure that we've been doing in New York City, and we still plan to use this in conjunction with our gray infrastructure approaches. And so finally, we are also looking at the impacts of intense precipitation compounded with sea level rise. We have a current project that's underway, which we anticipate releasing by the end of the year to characterize flood risk citywide. Our flood maps are based on coastal flood risk and with some riverine flooding, but this will be the first time where we've actually mapped inland flooding and sewer, where the sewer network and sewer constraints are incorporated. So we hope that this will be a tool to guide our future investments in both gray and green infrastructure, and what we've been calling blue-green, which is more of the Copenhagen approach. So next steps, we'll continue to work with the mayor's office as they refine the climate resiliency design guidelines. We'll continue to advance pilot projects and seek out opportunities to actually test the design guidelines, and hopefully continue to fill in the gaps working with the New York City Panel on Climate Change and others to get better information about rainfall intensity and to reconcile the design guidelines with these practical applications. And with that, I'll leave a couple links up on the screen. I also do want to give credit to Eric Rosenberg, who worked with us on the IDF analyses that I described earlier, and whose slides I borrowed from some of his prior presentations. So feel free to contact either one of us with questions. And with that, I guess we can open it up.
Thanks, Alan. I guess one of the first questions I have for you is how much pushback did you get from the various agencies when this first came out?
It's a good question. If I'm being completely honest, I think the biggest pushback was probably from my own agency. Initially, the guidelines were not really as focused on the on-site requirements, but also conveyance. And that's really been our biggest stumbling block, is that on conveyance, there's real sort of apprehension to adopting the projections, in part due to the uncertainty, as we've discussed about the sub-hour, or rather the sub-daily projections, but also because of the reality of changing the system, and that you can't just upsize one part of the system without a really wholesale revamp from the bottom up. Yeah. So from the other city agencies, as far as the on-site detention.
Oh, Sean, hey, from last week, how you doing? Pretty good.
Sounds like we're getting someone else talking on the line there, but as far as the on-site detention,
yeah, what's up?
Didn't really get
Sorry,
a lot.
I wasn't trying to ignore you, by the way, for your other things. I was gonna get.
All right. Everyone other than the presenter, please put your phones on mute. We're getting interference with other conversations.
Thanks. Go ahead, Alan. Sorry about that.
Yeah, so just to wrap up that thought, we didn't get a lot of pushback from the other city agencies as far as the on-site detention. And I think that's in part because, and retention, I think that's in part because their guidelines are not mandatory. It's been an experimental phase, and it's simply encouraging you and giving you tools to look at ways to maximize how much water you keep on your site at this point.
Other questions for Alan?
This is Lou again, Alan. Really interesting, and to upgrade one part of the site one part of the system have to upgrade all, and then the use of retention and green approaches to retain is clever. I just wanted to, and I don't know if this is a problem, but on slide 3, we say precip increases 0.73 inches per decade, and the distance between 1925, the midpoint of that period, to the current is essentially 100 years. So that would be 7.3 inches since 1925. Do we have any reconciliation that we need with slide 9, where we say IDF is essentially no change in the IDF, or is that reconciled by subsequent slides after slide 9? It just seems hard to have one without the other.
Yeah, it's a good question. So essentially, you're saying when the observations are that precipitation continues to increase, why can we sort of resolve to say it hasn't changed and therefore we're going to keep the current IDF? Is that essentially what you're asking?
Yeah, exactly. That is, since 1925, the midpoint of the turn of the century and 1950, the increase with slide 3's sort of rough estimation is a 7.3 increase in inches of rain. So that seems like, you know, kind of wow, and kind of also consistent with observation. So is there any trouble with reconciling that with slide 9, or just kind of help me over that hump?
Yeah, I think one of the, my immediate reactions is the fact that that is annual precipitation, or rather, sorry, daily precipitation. No, annual, okay, annual precipitation. So the intensity question comes up again in terms of, are these trends occurring at the very fine, small duration periods that we actually use to inform planning in practice. And I think the information that we've been getting is still that for the short durations, there hasn't been much of a statistically significant trend. But again, if you're, I think even if you're looking at the 90% confidence interval of Atlas 14, we could move towards a higher curve. There's been some really, it's been a sticking point though, and I think this sort of, I don't know if it's a cultural shift or what, around moving from historical observations to something that's more future oriented has been a real challenge, and I think one, I think that kind of warrants its own discussion, because there are some real challenges in change. Also, one beyond the feasibility of changing one part of the system, just even the practices of where intensity information appears in our rules and guidelines. It's really hardwired into and really deeply embedded in some of the ways that we actually apply them. So the barriers again to change are big, and something I think we continue to push against.
Got it. Thank you. And understand those barriers and challenges have a lot to do with cost, which this system looks like many billions. Yep,
absolutely. But I think we want to be opportunistic and really find, like through some of the example projects I've given, as well as, new capital build-out projects, sewer build-out projects, any opportunities we can to incorporate more forward-thinking projections.
Got it. Thank you.
There was a question that came in from someone listening online, Alan, just about what design storm is used for water quantity compliance in New York, if the design storm is based on the 24-hour event or time of concentration.
I believe those are based on the 24-hour event. I actually am not positive, and sometimes get, not working on some of these things in practice, sometimes get mixed signals on which ones used, but I believe it is the 24-hour.
Yeah, I think it's a 100-year, 24-hour design, a 10-year for conveyance, but for design of storm drains and catch basins and whatnot, time of concentration is typically used.
All right, any last questions for Alan or Art before we let them go?
Thank you very much.
Nice job. Yeah, thank you very much to both of you for joining us, and please feel free to hang out for the rest of our presentations today. But this was very helpful. I think it's always good to get some perspective from you know, on the northern reaches of the watershed, as well as kind of just outside in New York City. So we do appreciate your perspective, guys. It's a big help for us as we're trying to get rolling down here.
Great. Thanks for having us.
Thank you. All right, Dave, why don't you take us into the project update?
Yep, thanks, Norm. So this update is a little bit of an extension of the update that I gave back in December on the climate work that we're doing at CSN, specifically the recent stakeholder engagement survey that we put out. I'm going to spend a little bit more time today talking about sort of where we're going from here. I'm going to put a little bit of a bow on some of those results that I presented back in December. Talk a little bit more about the context behind them, and then again, kind of moving forward. So in terms of an outline, again, just kind of going through some of those major takeaways for the survey and sort of how you can kind of take a closer look at some of that, you know, kind of interweaving some of the key points on how we're managing current and future flood risk in urban landscapes, and then talk a little bit about what's next. So posted today, I guess, right, Allie, is a draft of sort of a first memo in a series that we're going to be putting out over the next 9 or 10 months or so. This first one is going to summarize the key findings from that stakeholder survey that we put out late last year, and that I'm going to be talking about today. The way that the survey or that the memo is structured, it talks a little bit about some of the methods and the responses that we received to that survey. Goes through all of the key findings, kind of broken out into the different sections, one looking at the overview of risks and concerns, one on current management and in some ways capacity, and then the third portion of it, sort of that forward-looking, kind of what are the key needs in terms of tools and information. In the appendices, there are the full survey results appended there, so if you are interested, as a reminder, the survey, and this is described in the methods, but there are actually two survey instruments that we use kind of with different levels of detail. One was a very targeted outreach to some key stakeholders. One was sort of a broader distribution to our network as well as some of the work group members. So both of those surveys are included in Appendix B, so you can feel free to kind of dig through those. There are still going to be probably a few tweaks and edits, and we'll let you know when there's a final version available, but please feel free to go ahead and take a look at that, and if you have any questions, I'd be happy to talk with you about it. So to just kind of go through some of the key takeaways that I really wanted to drive home that came from the survey and that are summarized in the memo. In terms of the concerns, the biggest concern really is that damage to public and private infrastructure, particularly the transportation network, our roads, bridges, and culverts that are caused by large storms. You can see the graph on the screen. These were sort of the top 5 most commonly cited. That number, the x-axis there, is the number of people that indicated that it was a top concern for them. So you can really see that damage to public and private infrastructure standing out. Right up there is the declining performance in our public and private stormwater management systems. So that could be from a quality standpoint in terms of how we're doing in achieving our nutrient and sediment reductions with those BMPs, as well as a quantity perspective, whether we're seeing failures of those practices that could pose other risks. Other ones that kind of come in pretty high are flood damages to public open spaces and stream corridors, as well as, of course, public health and safety, and then really pronounced, of course, in the tidal regions, the blue sky flooding, the sunny day tidal flooding events. So when it comes to, you know, talking about damage to public and private infrastructure, it's really important to kind of understand, and you all as the Urban Stormwater Work Group kind of understand this, but knowing what's at risk here, it's not just our stormwater BMPs that we tend to focus on through this work group, but it's the wide range of public infrastructure, including the sewer pipe networks, obviously the transportation systems that I mentioned before, you know, water pipe distribution, dams, the stream corridors, et cetera, as well as our private properties. Something that also kind of came through was an indication that there's going to be a lot of focus kind of moving forward on improvements in resilience that can help protect that transportation infrastructure because of its impact on public safety and public health. I think there are concerns about loss of conveyance capacity in some of our systems, as well as concerns about just the current resilience of our road, streets, and storm drain networks as they exist. So I think a focus on those areas in particular kind of came through in the survey. The second major takeaway, perhaps not a surprise to folks, is that everyone is concerned with how to pay for the necessary maintenance and upgrades as well as the plan for future resilience. So this graph here looks in particular, again, looking just sort of at the top 5 responses for the major concerns related to increased rainfall, increased precipitation on the stormwater BMPs. And, increased costs for non-routine maintenance stands out far and away as the number 1 concern. A lot of the other ones that kind of fall in right behind it, number 2 and 3, are also really tied to cost in some specific ways. Chronic routine maintenance problems for stormwater BMPs is a very costly enterprise as we move to more distributed systems. And then the trying to achieve pollutant removal and flood control performance with our BMPs is another kind of link to cost in a way. There are concerns about how our more distributed practices are doing for larger control events. And so, Tom and I use this a lot when we talk about our, maintenance programs, but this shift from the older inspection model of the one large stormwater detention facility that really is effective and, traditionally used for quantity control, but maybe doesn't provide the quality, towards our more distributed, LID kind of model, is something that folks are a little bit concerned about, I think, in survey results, as far as how they're doing for controlling both quantity and quality together, but also the cost associated with now having to inspect a much greater number within their inventory, and then inspecting those more often with these more frequent high-intensity events. So those kind of coming through clearly as well. In particular, with these extreme rainfall events, we are kind of expecting things like more instances of bed erosion, sedimentation, clogging up some of these practices, which might lead to less performance, particularly on the water quality side of things, as well as inlet erosion and issues like that that are going to lead to chronic maintenance concerns unless larger retrofits and overhauls are performed to kind of try to reduce some of those issues. The third takeaway, and this was another one that I tried to emphasize back in December, is that in general the respondents to the survey are not comfortable with the current quality and utility of the engineering design criteria that are available to them on future rainfall intensity. So, these are raw numbers in terms of the total number of responses, but far and away most folks feel that they need better information now for, whether it's how to design or size their practices, adjust their planning or their maintenance routines. They need better information. If they aren't saying it right now, they're already getting pretty concerned or getting concerned. There are very few who actually feel comfortable with the current engineering design criteria.
Those are usually white males of 65 years of retirement.
And so, again, this is to just drive home the point that, the stormwater volume targets to manage municipal risk, they're addressing a range of issues. It's not just the water quality, but these design criteria are used to, determine channel protection, overbank flood protection, as well as extreme flood protection. And while, historically and typically changes to the needs for sizing and to convey these storms is driven by changes in impervious cover and land uses across the watershed. While that is still certainly a major factor, I think we're concerned and seeing more and more that some of these may be climate-driven changes in the future. And then the fourth takeaway, I have 5 in total here, but that basically any tool as we start to look forward is useful, but you know, sort of the message was if we need new designs, give us new design specifications rather than sort of a piecemeal approach. So, you know, when we asked folks what would be most useful if you needed new design specifications, most commonly people just say, give us new revised techniques and specifications. It's sort of the full package: sizing, conveyance, storage, overflow, materials that we should be using to improve the resiliency of our practices. Coming in second is a focus on planning guidance. So how do our BMPs, our floodplain management, and conveyance systems work together? I think Alan's presentation on some of the approaches that are being taken in New York City are sort of a good example of the way that they're kind of looking at that, how those integrated systems can work and get some guidance to that effect. There's also definitely interest in looking at improved or updated intensity, duration, frequency curves, both for historic updated curves for the frequent events, as well as the projected IDF curves for future years. Again, I don't want to give the impression that they are not welcome. You can see the number of responses that, you know, folks said they're useful here. It's certainly well over half, probably about 70% of responses indicated these tools were useful. Just a slight preference for those kind of full package kind of products. And the last takeaway that I didn't really have a chance to mention back in December, but after kind of digging through the results a little bit more, the responses were really, actually kind of surprisingly to me, very consistent across community sizes and geographies. There are a few slight differences, and I'll talk about those in just a second. But really, it's kind of, if you go in with a magnifying glass and look closely, it's kind of parsing out some of the slight changes. Something that was a number 1 priority might have flipped to a number 2 or something like that, but not a lot of major swings if you look at Phase 1 MS4s versus Phase 2 or non-regulated stormwater communities. If you look at headwater states versus, you know, bay or tidal states. So the couple of things that did kind of come out, if you looked at it a little bit more closely, I think first, not super surprisingly, the headwater states and the smaller communities both sort of magnified the constraints around cost and resources. I think that came out in some of their preferences for future tools. You know, small communities, for instance, were more interested in looking at ways to ease their ongoing routine and non-routine maintenance burdens, you know, whether it's staffing constraints or guidance for how to do those inspections and corrections to improve their resilience, as well as planning guidance to try to get out in front of things. Whereas, you know, some of the larger Phase 1 communities typically were a little bit more interested in retrofitting their existing practices. They were looking at, you know, new IDF curves for adjusting the sizing of their BMPs, or just new and innovative technologies or practices that they could use to retrofit some of their legacy practices, or the ones that may be undersized or more at risk. The one other thing, well, I didn't put it on this slide, but I think I mentioned it before, that the tidal community versus non-tidal split. Tidal communities, the blue sky flooding issue jumped out to basically the number 1 concern, whereas it didn't really show up as nearly as highly, of course, for the non-tidal communities. The one other piece is that there was kind of an interesting slight split in terms of looking for projected versus updated historic IDF curves. Some of the state agency respondents, or the stormwater agencies, the resource protection agencies, seem to be a little bit more interested. The projected IDF curves ranked ahead of updated historic IDF curves, whereas the local government respondents, both Phase 1, Phase 2, and non-regulated, tended to have a preference for updated historic IDF curves, especially for those more frequent kind of 1 to 10 year events. So again, these are all very slight differences, kind of around the edges, but something that I thought was worth calling attention to. So in terms of what's coming next, again, I mentioned in terms of that memo, it just went up today as a draft for you all to take a look at and review, and I'd be happy. It's not sort of I don't have a formal comment period in mind, but perhaps maybe by, you know, 2 weeks or so, if you have any comments on that, and you can send them to me I would have to look at my calendar to see what a good date is for that. But if we have about 2 weeks, if you do want to chime in, I'd be happy to talk with folks and take any comments that you have. Looking ahead, there are a couple of more memos that we are looking to produce over the next 9 to 10 months or so before the end of this year, sort of in a multi-step process to kind of to drive us towards some next steps for the Urban Stormwater Work Group as well as the broader Bay Program folks. The second memo in this process is really going to be sort of a state-by-state summary of the current engineering standards. So, you know, the table on the screen is sort of an example of all the different management objectives that are being achieved using these different design criteria and engineering standards, whether it's water quality, channel protection and conveyance, you know, dam and bridge safety, et cetera. And so just making sure that we have a good understanding of where all the states are, what the guidance are, you know, is it's available to local communities for design, so that we know that when we produce future tools and products, they're useful. We also have a sense of, you know, who is in the process of updating their manuals for the states that are looking at doing something like that. I am working now on getting around and trying to talk to as many of the state agencies as possible. So if you haven't heard from me yet, you may be hearing from me soon. I'd love to get an update from you all on that as we move forward and have a good summary there. The third memo in this series is going to be really looking at the current science on local precipitation projections. So this will be taking, first of all, some of the Bay Program's climate assessment findings, specifically focused on rainfall volume and intensity that you're going to hear from GoPaul sort of in draft form, you know, kind of initial assessment findings today. So, you know, a summary of that for folks, as well as a discussion of the different efforts to downscale and project IDF curves around the watershed. You've heard some of what New York has been up to. There are other efforts in Maryland, in Virginia, I believe, and maybe in the districts as well. So trying to round all that up and make sure that it's available to folks. And along with the science piece of it, try to tie it as best we can to what those design and management considerations are. Much like Alan talked about, some of the challenges, for instance, getting to sub-hourly projections and how that can be managed and the importance of some of those pieces. And then finally, the last memo that we'll be looking to put together will be looking at the BMP vulnerability analysis in particular. So this is, again, sort of a synthesis of what is available. To some extent, there is not a ton of research in this area, so some of it, you know, may be really just thinking about the way that our stormwater management systems, conveyance systems function to identify areas that are at risk, to the extent that we can identify potential impacts on pollutant removal performance. We'll try to do that, try to identify some best practices for improved resilience based on work that others have done. Looking at both some of our traditional stormwater practices as well as our, you know, I'll call them our Bay BMPs, some of things like stream restoration or our gray infrastructure repairs and things like that. So, you know, there's a lot to go. We'll be working with members from the work group as well as other stormwater experts around the watershed to kind of drive at these different questions through different steering committees. And again, I'll be kind of giving updates through this venue as we go along and keeping folks apprised of what we're doing and making sure that we're getting the tools and the information that folks need. So anyways, I just wanted to give you a sense of this survey. It's sort of not the end of the road, it's the beginning of the road in terms of what we're hoping to produce to provide some guidance that eventually, hopefully, will turn into sort of a multi-year work plan for tackling some of this that the Bay Program can take on and run with. So with that, I will just kind of stop there. I will take any questions either on the survey or some of the next steps that I just talked about. And if not, we'll keep plugging along.
Any questions for David?
Great job. Really interesting. I remember Churchill's statement on a different subject. It was of some magnitude, but he had said, this is not the end. this is not even the beginning of the end, but maybe it's the end of the beginning, which is, I think, pretty much where you guys are, and a useful beginning, too. I mean, memos 1 through 4, I think, are going to make a really nice contribution, and I'd like to hear what the program thinks about this, what the work group thinks about this. But one thing that would be useful is, do we anticipate memos 1 through 4 to be over the next year? That is this a 2020 product? And I say that because the management board, the water quality GAT, under the direction of the PSC said, man, we've really got to do something. And it would be great to be able to demonstrate to them as we progress. Look what we've done, over, say, 2 quarters from now, 3 quarters from now, 4. This is the really good start. So what's the projection? Is it?
Yeah, the plan is to have all 4 of these.
That's good, because then you'll have the observed projected precipitation.
Yeah, I think our hope was to have them wrapped certainly by the end of this year. I think we were our optimistic goal is maybe October for the full set. I think, the hope is to roll them out kind of one at a time. Maybe I think that the BMP vulnerability piece is probably the longest effort and sort of the save for last piece of it. I'm hoping, and I don't want to overcommit, but I think the state-by-state summary should be something that will be a relatively quick turnaround, maybe a couple months. But yeah, the goal is by the end of the year.
That's great.
Hey, Lou, one of the things we could do is, I hate to add to David's presentations list, but we can certainly give the management board a briefing every once in a while as we come up with finished products for the memos.
I think that would be fantastic. Yeah. Yep. Because this has caught the practicing community's attention. It's caught the management community's attention, and so I think the management board would welcome that. So think about a time when you feel there's some significant report out period, maybe memo 1, memo 2, or whatever you think. And Norm, I guess you and I can help set that up for water quality GET usually first, and then management board.
Yeah, we could always bypass the GET though.
All right, both.
All right, let's. In terms of comments, I know David was a little loosey-goosey. I will say that I would like everyone to get any comments that they have to David by close of business February 7th. So that'll give you like 2.5 weeks to get comments to David. All right, Dave, thank you very much. As usual, good stuff. Mr. Linka, would you like to introduce Gopal? Everybody pretty much knows you, but I'm not so sure we've had Gopal in front of us very often.
World
famous. Yeah.
That's better.
It would be my pleasure. Gopal has been driving the watershed analysis for the Bay program as the lead practitioner for many years now. He had put together the Phase 6 assessment, which had one of its major aspects, an assessment of climate change in the Chesapeake watershed. And there are some useful and interesting results in terms of discovery. As we entered into the work, we uncovered this information largely through observations, taking a careful look at the research, taking a careful guidance from our scientific and technical advisory community under constant sort of vetting and review by all of the Bay program management groups, and then the model. So the observations, research, and model. So and Gopal will share some of those findings now.
Thanks, Lou, for that introduction. And Dave and Norm and Carl for inviting us to present this work that we have been doing to the Urban Stormwater Work Group. So I'll be presenting our initial findings from the Phase 6 climate change assessment model work that we have done. To get started, here is a brief outline of the presentation. I will very quickly summarize some of the overview aspects of this work, also present the inputs and the methods that were used in the putting together this modeling work. And then I will get into some of the climate assessment results and initial findings that we have, and we will go through finally some of those results and get into the understanding and explaining aspects of these models. So I'll point out that I have more than 20 slides here, but for many of them, I will skip through them very quickly to emphasize some of the important aspects that are presented there. But I'll be happy to take any specific questions that may be needed for further clarification. So for the Chesapeake Bay Program Climate Assessment, in this work, the direction of Chesapeake Bay Partnership decision makers, the guidance of SAC and its workshop recommendations, several decisions, key decisions from the modeling work group and climate resiliency work group, and stakeholder collaboration were collectively applied. And we will be seeing many of those aspects throughout this presentation. So first, to get started on some of the inputs that were used in the model, we had specific recommendation from STAC as well as modeling work group that our 2025 climate change assessment should be based on rainfall data that was linked to observations. And specific recommendation was to use as long of a period that was available for estimating the trends information that can be applied for estimating change in rainfall for this modeling work. And when we are talking about the change in rainfall, here we have a very specific meaning behind that, which has to do with the average hydrology period of 1991 to 2000, which is used for the TMTL assessment, and then the climate change assessment period specific to 2025 here will be a 30-year change between the 1995 condition and the 2025 condition. So we put together this assessment for all of the counties across the watershed, and the spatial figure, the spatial map, is showing that the variability in estimated change over that 30-year period. And what we see here is, of course, the changes in the rainfall volume over that 30-year period for all the counties. But we also have a summary of that change in rainfall summarized over some of the major river basins. So for the watershed, the 30-year change was estimated around 3% increase in rainfall volume. But we do see some spatial variability across the basin. And in our opinion, what stands out is that Western Shore, which is one of the areas where we have high amount of urban and developed areas, had one of the highest increase in rainfall volume, about 4%. So this is a summary of rainfall information that we are using in the for 2025.
Yeah, thanks, Gopal. So higher in the north, lower in the south. You can see an interesting orographic band in the Shenandoah Mountains where there's sub-county scale. And the Western Shore, that developed basin of the Western Shore, most developed basin of what we see here, and also the international headquarters of CSN, they win at 4.1%.
We change more than anybody else.
More problem. Well cited.
Thanks, Lou.
Plug for the international headquarters.
And maybe I missed pointing out, so we are using this 80-year worth of data set for estimating these trend information, as it has been shown, for example, for these two counties, but it was done for all the counties. So this was not an input, but we think that this is an important slide to put things in context. So we just talked about the change in rainfall, but this slide is showing how the stream flow has changed over this longer period, and specific in this slide over 1940 to 2014, which was used in this assessment, a joint assessment by USGS and EPA report that came out in 2016. And in this work, they used what they call, or what USGS calls, is hydroclimatic data network, where they use watersheds which are classified as natural. So we don't have some of the changes, man-influenced changes, such as withdrawal and things like that. So it gives a more robust assessment of how climate is influencing the stream flow. And what we see is similar to the rainfall trends that we saw, is also seen in stream flow, where we see increases in stream flow volumes across the watershed, somewhere between 1 to 10%. And again, what stands out is some of the western shore areas, or where we also saw higher amounts of precipitation. It did result in higher increases in the stream flow volume. And this study was corroborated by a recent publication that came out from the USGS as well, which was from Karen Rice and others, which also estimated increases in the rainfall volume as well as stream flow, in many areas with significant statistical significance. So in next few slides, I will be going a little bit more into details about the precipitation and temperature changes. So we mentioned that for 2025, which is shown here on the left panel, we are using trend-based information, but we also have, just for corroboration purposes, results from various GCMs for different emission pathways that are described very nicely this morning. But for way down in the future, in the realm of 2050, we are entirely relying on the information from GCMs. And what we see here is, as we move from lesser emission pathways to higher emission pathways, representative concentration pathways of 8.5, the wetness of the rainfall increases. So the rainfall volume increases from about 5% to almost 7% across these RCPs.
On an annual basis.
On an average annual basis. Thanks, Tom. So that was estimate from different GCMs average over the watershed. This figure is to give us a sense of how GCMs have that spatial information, that average watershed information disaggregated over the watershed. And the main point that I want to make here is that we have these 31 different GCMs, but they have slightly different estimates for how that volume is increasing across the watershed. Some GCMs have estimates higher in the northern side of the watershed versus the south of the watershed. Similar figure as before for the temperature in this one. So we have an estimate of around 1 degree Celsius increase between 1995 and 2025 for 2025 conditions. And for 2050, we have around 2 degrees Celsius increase. Similar to the rainfall, GCMs disagree on the spatial pattern for the temperature increase. But there is a level of consistency among many of them, which suggests more warmer conditions as we move away from the ocean with higher elevation, of course. So putting the rainfall and the temperature trends together, both from observation-based trends and with the ensemble estimates from GCMs. So we have an estimated increase across the watershed for all these conditions for 2025, 35, 45, and so on. We are, at the recommendation of STAC work group, the STAC and modeling work group, we are using a trend-based estimate of 3%. And for 2055, entirely relying on the GCM, which is about 6 to 7% increase in rainfall volume, and a hybrid approach for the periods in the middle, where we are combining both GCM and trend information together. So as Tom pointed out, those were the estimates for average annual change, but watershed model simulations are made at hourly time scale. So we have this disaggregation, temporal disaggregation in between, which is based on the work that was put together by Grossman and others, where they analyzed 100 years of rainfall data, and where they found that majority of the increases in rainfall volume has occurred in the top 10% of the rainfall events. And that is the information we are using for disaggregating average annual rainfall all the way to hourly time step. Here's a quick summary of inputs that we are using in our 4 assessment periods, 2025, 35, 45, and 55. And the main point here is the volume is incrementally increasing across these periods, from 3 to 4 to 5 to 7 for these 4 assessment periods. And a quick slide for temperature here. Temperature is also estimated to increase as we move further in time, starting about 1 degree Celsius for 2025 to 2 degrees Celsius at the end of the century, middle of the century, around 2035. In this assessment, we are also using some information on land use change as well as population change. These percent changes are represented here with respect to 2010 condition. So these are in some ways very specific to how the program assessment was done for the climate change and the land use change. I won't get into the details, but here are the numbers for both land use change and the population change. And I will note that population is estimated to increase significantly and has some impact on the nitrogen levels. Okay, so before we get into the model results, I want to emphasize some of the limitations and areas of uncertainty. Of course, as we saw, there are some uncertainties because of the climate projections, and we anticipate some from the delta method, or also describe different methods which lead to somewhat different outcomes in rainfall, how we are applying the intensity and PET methods, and then the model uncertainty, the way our model works. Also, stormwater as well as other BMP efficiencies are held at the constant level for all these future assessments, and hope is that we would be able to refine as better information comes out of the work that this work group is doing. And this last one is more specific for some of the future scenarios, and what I mean is 35, 45, and 55 one, because we have seen some of the changes already when we are talking about the assessment of 2025. We're only 5 years away from the 2025 condition. And all of the practices and agricultural related changes are already included in this assessment for 2025. So next few slides will show us the watershed model results for these climate periods that we just talked about. So we will be seeing the effect of these changes in rainfall and temperature on the water quality, and specifically how the nutrients and sediment loads are estimated to change. This is one slide summary of 4 important parameters: the freshwater delivery, the nitrogen delivery, the sediment delivery, and the phosphorus delivery for these 4 periods that we have been discussing with respect to the condition in 1995. So, for example, the nitrogen, we estimate around 2.6% increase in nitrogen delivery for 2025 as compared to the 1995 estimate. And about 10% or 11% increase in nitrogen delivery under 2055 condition. But main point here is that we do estimate with increasing rainfall volume or the wetter rainfall volume, an estimated increase in all these loads across the watershed. Tom?
A quick question on the sediment delivery. Is that due to a land use effect, or is it a stream bank erosion effect from the stream segments?
Thank you for that question, Tom. So what we are seeing here in these plots, since these are delivered loads, we have estimated increase from erosion on land, some downstream effect on stream bank erosion, following the framework that we have for the phase 6, and the effect of increased flow and also the intensity when that flow is increasing in the rivers where they cover more. So all those 3 effects are combined here.
Thank you.
And to be clear, I think, correct me if I go off track here, Gopal, I think these all use 2025 land use. So there's no change in land use as we go to 35, 45, 55 climate.
That is exactly right, Leo. So all of these scenarios on this slide are simply due to the changes in climate, the rainfall volume, and the temperature.
So you're exactly right, Tom. This is the landscape and especially the river systems trying to get into equilibrium with the new hydrology they're delivering.
And some of it can also be increased wash off.
Yes, yes. Oh, absolutely.
Impervious surfaces.
Right. That's why I say landscape and river system. Yeah. Right.
Thanks, Lou. So this next slide simply adds the estimated effect on top of the estimated climate effects, but emphasizing here that from estimated changes due to the land use change.
Yeah. I mean, I don't want to steal any of your thunder, Gopal, but this is pretty, to me, a little jaw-dropping in that through all of the history of the VAE program, we've been very arm-wavy about, we've got headwinds, we've got challenges, we've got to deal with land use changes, and basin-wide. Now, land use changes, of course, on a local scale can be really profound in terms of streams, no doubt, but in a Chesapeake watershed scale, the real headwind, according to this presentation of the information, has been the change in precipitation, hydrology, and land use, of course, is a contribution, but within a model system you can parse out those differences. That is, our hand-waving on it's land use is a real challenge is really dwarfed by the challenge we didn't really have a good quantification for, say, a decade ago.
I've been spending my whole life fighting impervious cover, but now I have to shake my fist at the rain.
Stupid rain. Just tell it to cut it out, Tom.
Thanks for that point, Lou. moving on, and I realize I'm running a little short on time here. So now we are moving away from those 4 assessment periods and focusing on 2 periods to kind of cover the envelope of the period that we are looking at. So these are the same numbers from the previous slide, but we have some more descriptive details for the speciation aspects of nitrogen and phosphorus. And main point here that we want to make is that although there are significant increases due to climate between 2025 and 2055, but a significant chunk of that increase, in case of both nitrogen and phosphorus, are in the particulate form, which have relatively less of an adverse effect on the water quality in the bay. So that is a little bit of maybe a positive news in the face of significant increases due to the climate for both 2025 and 2055. So now we are changing gears a little bit and trying to explain some of these results, and this is meant to be a transition slide for explaining some of those results. What we are seeing here is an estimated change in the flow regime for the Potomac River Basin. And we are estimating those changes for these 5 different quantiles. And it is very obvious here that the top 2 quantiles, which is to say the top 40% of the stream flow events or days, has increases in flow for both 2025 and 2055 conditions, whereas the low flow conditions, the bottom 60% of the days aggregated had a decrease in the rainfall, decrease in the stream flow volume for both 2025 and 55. And what we can, just based on this analysis, expect is what we just saw in the previous slide, that more energy increasing the transport capacity of the rivers and increases in the delivery of the particulate form, which we are calling the increases in riverine nutrient competency. Same as the delivery of sediment is increasing, we are also increasing the delivery of particulate nutrients. So this is the slide which is kind of making the point now, but in terms of the loads. So we have more scour in the rivers, and therefore more scour of nitrogen material for increasing from 1995 to 2025 and 2055. Very quickly getting into the 2 different scales that Bay program looks at the data for the model estimates. Edge of the river loads for 2025 and 2055, flow, nitrogen, phosphorus, and sediment, and also highlighting the sectors. So these are, in the dark black color, are the estimated increase in the delivery from the developed sector. So this can be seen as the area of opportunity for reducing load that are specifically introduced from those sectors because of the climate change effect. So these were the edge of river loads. So as Tom kind of pointed out earlier, that these are the estimated effects because of the changes in the land processes and the stream processes. And then these are here the delivered loads, which are emphasizing the changes in the riverine processes, which also adds to the increases in the delivery. Back and forth, of course, the scale is changing, but the numbers kind of paint that picture that how those load changes are coming about. Here's another way of seeing the same information, but I have only that for 2025. For nitrogen here, getting into a little bit of details about some of the riverine processes. And the main point here that I want to make is, for 2025, majority of the increases are from the landscape. Some are from the river as well, but the land and stream effect simply dominates the response. By 2055, that is not the case anymore. The riverine processes are also significantly important, maybe to an equal extent as of the landscape and small stream responses. So they both are important mechanisms for the climate change response. To summarize what we just talked, maybe 4 bullet points. Of course, the progress has been made in the Chesapeake Bay restoration, but what we saw in terms of increases in nutrient loads and sediment delivery, the wetter, the warmer, and more crowded future adds additional challenges. We also saw that the future climate adds these increases in delivery, which are due to both land and riverine processes, changes in both land and riverine processes, and the relatively higher proportion of particulate nitrogen and phosphorus are estimated under better climate conditions, and due to the more transport on the riverine side and higher riverine nutrient competency as a result of that. So these are the 4 summary points, and that is where I'll end.
Thanks, Gopal. Lou, any closing comment on that? Or Gary?
Gary had another commitment, but I would say that this is the assessment of future climate risk to Chesapeake water quality standards. There will be implementation plans designed for that 2025 outcome. Perhaps there would be other assessments by decision makers in the future. This will be sometime probably within the next 18 months. These decisions will have been made, and then we put together the WIPs for the 22-23 milestones. Perhaps even adoption of beyond the 2025, perhaps the 2035 findings. Much is already being applied based on these findings in terms of the plans of the Bay program. But the most important discussion that this work group, I think, could have based on where these findings stand today would be how can they contribute to memo 3, 4, and 5, 2, 3, and 4. I mean to say, I'm not going to add another one.
No, thank you. Please.
You're good. Tricky. That is, how do we get to application? So you guys have, that is Tom and David, you have put us on this path that we need to be going down. How do we complete that path with consideration of this as a potential contribution?
Yeah, I think this is really useful framework, and I think it'll be part of the at least memo 3 in terms of the impact. But what the urban work group needs to look at is, all this work was done with the assumption that BMPs were constant in their efficiencies, and the question is, do the BMPs under the face of more runoff and warmer temperatures perform better, the same, or worse?
Right.
And that could be big of a delta effect as some of the things that Gopal was thank you, Gopal. That was a very great presentation. It's like the 4th time for me to get it. Thank you.
Yeah, and for everyone else on the phone, this was what you see from Gopal today was basically a peek under the hood. There is a ton more information that he simply just did not have the time to present because we asked him to do basically an overview. But sitting through the modeling work group meetings and seeing all of this, it became fairly clear to me that this is a fairly daunting prospect that we're going to have to address. It basically completely erases everything we've done. If we don't address it in a manner in which we take into account what the research is telling us. So I'll stop there and ask, does anyone have any other questions for Gopal or for Lou? All right, guys, thanks a lot. I know it was kind of rushed putting this together based on our conversations at the last meeting, and I know everyone really appreciates it. Taking a look at the time, what we'll go ahead and do is we'll push the urban BMP crediting practices off until February. Our next conference call is scheduled for February 18th. We'll get a draft agenda. We'll get an agenda out to everybody like we usually do a couple of weeks in advance. I can say that I did hear from 2 or 3 of the states on the crediting process. I would like to hear from the rest of the states on what they would like to see, and also some of our local government reps. Make sure you guys get your comments into us. We only have the ability to work on a couple of things. Thomas still has his hands full with the stream restoration, and as you saw from today, David definitely has his hands full with the climate change stuff. But we should be able to work on 1 or 2 things at best. So please get your comments in on what you think the priorities should be, and we'll talk about it at the next meeting. Does anyone else have anything they want to add for today? Okay, hearing not, we'll go ahead and close the meeting out. Want to thank everybody for their participation today. We will talk to you all soon.
Thanks, Norm.